All right, here we go. 10.3. Now, today we are going to talk about constructions. And if you'd like to do the constructions, you can for practice. But the real reason for today is the results of the constructions that we will talk about. What is your homework? All right, here we go. So 10.3 is something called concurrent lines. This might be vocabulary-wise, this might be one of the more challenging sections of the chapter. So hopefully you're doing okay on the constructions. Remember, the test is going to be to do the constructions themselves. So we take a slight break on actually learning new constructions today. We're going to use the knowledge of those constructions to talk about a combination of the constructions. So very confusing vocabulary today. Make sure everything goes in your book of truth. There's going to be 4 concepts. So 1, 2, 3, 4. And for each concept, we're going to get vocabulary words. These vocabulary words are not very descriptive. They are the correct vocabulary words. They just don't help you. Some vocabulary words are very descriptive in what they do. None of these are very descriptive. Nobody keeps these vocabulary words straight in their head. So having these written in your book of truth will go a long way. Okay, here we go. Before we get to the concepts and the new vocabulary words, think about this. If you have 2 lines on a plane, those 2 lines can, think that one through, 2 lines on a plane, so a flat surface. If I draw 2 lines, well, clearly they could intersect, right? Or they could be not intersecting, and we would call that parallel. All right, keep that idea in your back of your mind. And now let's talk about what if you had 3 intersecting lines on a plane. Now, if you have 3, not 2, but 3 intersecting lines on a plane, it turns out 2 things can happen. So what does it look like? And it turns out that 2 things can happen, right? So one on the left, one on the right. So flavor 1, flavor 2. So the first thing, if 3 lines intersect, well, maybe this is what you had in your mind right here. But there's another thing that could happen if the 3 lines intersect. I never said they intersect at the same point. So these 3 lines also intersect. They just don't all intersect each other. All right, each one of those lines there intersects another one. So we would say the 3 lines intersect, just not all at the same point. So it turns out that we're more interested in the one on the left than the one on the right. So the one on the left, it's that one right there. That idea of where lines intersect at one point, that is this definition word called concurrent lines. So concurrent lines are 2 or more lines. We're going to be doing more than 2 today. 2 or more lines intersect at a single point. Okay, so 2 lines can be concurrent, obviously, but so can 3. So those are your 2 examples right there. So what would be a non-example? Here's a non-example. So here are 3 lines that intersect, just not at the same point. So we would say those are non-concurrent lines. All right, so today's class is going to be about, it's going to be about triangles and those concurrent lines. So combine triangles with concurrent lines, and the concurrent lines, the intersection is going to occur inside of the triangle. That's the idea today. All right, it turns out that can happen one of 4 ways. So each one of these is a concurrent line example inside of a triangle. They're each made a different way, and each one of these ways that these concurrent lines can happen gets a special vocabulary word. That's why it's confusing. Okay, so here we go, one at a time. So what would happen if I took a triangle, and let's see, a triangle has 3 vertices, and I were to bisect each one of those angles. So remember, this is that one construction for angle bisectors. So if I intersected each one of those, or bisected, sorry, cut in half, each one of those vertices, in other words, I made angle bisectors, what would happen? So it turns out that they would all intersect and they would be concurrent. Now I got to prove that, and I'm about to do that. So that's what we're going to do here. So here's the proof that the 3 angle bisectors of any triangle form a point of concurrency. So let's see, I've got a triangle ABC, and I've got the bisectors of the 3 angles of the 3 vertices A, B, and C. And I'm trying to prove that the angle bisectors intersect at a point, and I'm going to get a so what from this. it turns out that that point of concurrency where these three angle bisectors meet is equidistant to the three sides of the triangle. All right, pretty bold claims. Let's see if I can prove that. All right, so the first thing I'm going to do, hopefully this makes sense to you, I'm going to pick two of those angle bisectors. So I'm going to pick angle bisector of A and B. I could pick A and C, it doesn't matter. So I'm going to pick the angle bisector of angle A and angle B, as you can see those lines right there. And I'm going to extend them until they, in fact, do intersect. Okay, so you can imagine that they would intersect. Now I'm going to call that point of intersection point I. It's just a construction, right? Make angle bisectors. And now what I would like to prove is that the angle bisector of angle C also intersects at point I. So that's what I got to prove. So here's how it's going to do. Here's how it's going to work. I'm going to make from point I, I'm going to make perpendiculars. So we had that one construction that said from a point not on a line, make a perpendicular to that line through the point. So from I, I'm going to go perpendicularly straight down, and then perpendicularly to the left and to the right, so I intersect segment AC and segment CB. Now, I can make those. Those are pretty simple to make, and I could use that construction. Okay. So, by the way, if we're measuring perpendicularly to the sides, that's how we measure distance. If I could somehow prove that IT is equal to IS is equal to IR, then point I would be equidistant to the three sides of the triangle. That's one of the things I'm trying to prove here. But I also have to prove that the angle bisector C intersects I. So I got to do both of those. Now, this is pretty slick. And I'm going to write the statement right here. I'm going to immediately claim that they're equal. And then I'm going to do a little bit of drawing here to show you how this works. So let's see. Why does this work? Why is IT equal to IR? Well, IT is equal to R because we had this way back, chapter 3 said that if you have an angle and you make an angle bisector, that any point along the angle bisector, any point that lives on that dotted line right there, which I just defined as an angle bisector, is equidistant to the two sides of the angle. And remember, we drew way back chapter 3, we drew this. So if you live on an angle bisector, you are equidistant to the two sides of the angle. Well, if we just look at this piece right here, that's the construction that we have. Therefore, IT must be equal to IR. Turn your head to the right, now look at angle B, and it's the same construction, just reverse of the previous one. So therefore, we can say that IR is equal to IS for the same reason. Right? If you live on the angle bisector, then you're equidistant to the two sides of the angle that's formed. All right, so that's way back. That's a chapter 3 thing. It says any point on an angle bisector is equidistant from the two sides of the angle. Okay, cool. So I've actually already proven right there in that one statement, I've proved half. So I just proved that the point is equidistant to the three sides. Well, no, I haven't. Wait a minute. I did not prove. I just proved two of the sides. So where does the third one come from? Well, the third one comes from how this is written right here. So it says IT is equal to IR and IR is equal to IS, then therefore by the transitive property, I could say that IT is equal to IS, and there's that first half of the proof. So let's see, what did I just prove? I just proved the first half right there that says in the prove part that are equidistant to the three sides. So the last thing I simply need to prove is that angle bisector C actually intersects at I. Well, if it's an angle bisector, it means that you live, or that any point along the angle bisector is equidistant to the two sides. And I already proved that IT is equal to IS. Therefore, that angle bisector must go through point I. So I'm going to say it has to live on the bisector of C, since I've already shown in the previous two statements that IT is equal to IS, or the previous statement, I should say. And that was the last thing I had to prove. So as shown, I have now proven that. Okay, so if you got a little bit lost in that proof, it's okay. So let's see. Oh, I actually got to erase this. If you got a little bit lost there, it's okay. I'll clear it up for you nice and clear. let's see what we just proved. Well, what did we just prove? This is this theorem, and it says 10.1, and it says if you make the bisectors of the angles of a triangle, that's the vertices, then they all meet at a point, and that point is equidistant to the three sides of a triangle. So I'm going to talk in colors here. So let's see, the setup here is the black portion. So if I make the angle bisectors of A, B, and C, then those three angle bisectors have a point of concurrency, that's point I there, and point I, this is the red part, is equidistant to the three sides. So here's what I usually say. If you draw the bisectors of A, B, and C, then they intersect, and that point of intersection is equidistant to the three sides. In other words, IT is equal to IS is equal to IR. And there you go. That's that theorem. Okay. Now, I said there was going to be 4 concepts and 4 vocabulary words. So here's concept number 1. If you make the angle bisectors, you're equidistant to the three sides of the triangle. Well, we need a name for that point. Here we go. That point of concurrency where the angle bisectors intersect is called an incenter. So an incenter is the point where the angle bisectors of a triangle are concurrent. And if you also wanted to add to this that point that the intercenter is equidistant to the three sides of the triangle, you can do that as well too. That's also included in the theorem. All right, so that's the first one. That's the first concept, and that is the first first vocabulary word. You're like, well, isn't concurrency or the point of concurrency, concurrent lines, isn't that the first vocabulary word? Well, these are the ones I'm talking about. So I guess it would be more accurate to say 5 vocabulary words today. All right, so 1 down, 3 to go. 1 down, 3 to go. And remember, the red is the so what. So if black, then red. So if you make angle bisectors, then what's the so what? Then you're equidistant to the three sides of the triangle. All right, so if black, then red. All right, 4 concepts, 1 down, 3 to go. All right, remember, this is only going to be about triangles today. So what would happen if I took a triangle? I'm not going to make angle bisectors this time. I'm going to take the 3 sides of the triangle, and I'm going to make perpendicular bisectors. So once again, I'm going to prove this to you. It turns out that if you make the perpendicular bisectors to the 3 sides of a triangle, they all meet at one point, and that point's going to have a name, and we're going to get a so what to it. All right, so here we go. So I got a triangle, and I got 3 perpendicular bisectors. This proof is very similar to the previous one, and it starts off simply by extending 2 of those perpendicular bisectors. So I'm going to extend the perpendicular bisector of AC, and I'm going to extend the perpendicular bisector of CB. So in other words, I'm extending that one, and I'm going to extend that one. Now, clearly, if I were to do that, well, they would meet, and that meeting point I'm going to call point O. Okay. So let's see, what am I trying to do in this proof? I'm trying to do 2 things. I'm trying to prove that all 3 of the perpendicular bisectors meet at one point, and this is the other half. I need to show that it's equidistant, not to the sides, but to the vertices. So this is going to be the so what, that point of concurrency is equidistant to the 3 vertices. Okay, so let's do that. So I extended the 2 sides, they do meet, and I need to be able to show that they are equidistant to the 3 corners. So I'm going to make those segments right there. I'm going to connect O to C, A, and B, okay? And that's just a construction, right? That's just basically drawing a line. All right, here we go. So let's think. I'll draw this out for you real quick. Pick any of those 2 and think about this. If I have a line and let's see, I connect the perpendicular bisector and pick any point along the perpendicular bisector, that means this is equal to this. Poorly drawn, but you get the idea. So any point along the perpendicular bisector, this is that other part of that theorem that I mentioned in chapter 3, that you are equidistant to the 2 sides. So I can immediately say that OA is equal to OC, and OC is equal to OB for that very reason. right? I mean, look at the construction, right? You live, or the point O is on that perpendicular bisector of AC and BC. So therefore, you must be equidistant to the corners. And if we look at the statement we just made, let me clear all that out. If we look at the statement we just made, it's that same transitive thing as well, too. OA is equal to OC and OC is equal to OB. Then by the transitive property, right, you can see it right there directly above it, then OA is equal to OB, and I'm halfway there, right? I just now need to prove that that last perpendicular bisector, the one on the bottom there, AB, right, the perpendicular bisector, that actually meets in the center. And once again, it's the same reason. And the reason is, I'll draw it for you one more time. Well, what is that? I just made a perpendicular bisector. So I know that I am always going to be equidistant to the endpoints of that segment. And since point O, right, is that point, well, then it has to go through it, right? O lies on the perpendicular bisector. It has to lie on the perpendicular bisector. Okay, so we did it. We proved those two statements right there, right? So let's write this one down. So this one says that, let's see, now here's the construction, if black then red again. So what is the black portion? So let's see, if you make perpendicular bisectors to a triangle, that's the black portion. The then part of it, that is, well, then you are equidistant to not the three sides, but to the three vertices of the triangle. In other words, OA is equal to OC is equal to OB. So if black, then red. As always, pause, I'm moving on. All right, so I also said that each concept, that was concept number 2, each concept gets a name, and the name where the perpendicular bisectors meet together is called the circumcenter. All right, so the circumcenter is where the perpendicular bisectors meet, and the so what, the if black then red portion, right, is that circumcenter is equidistant to not the three sides, but the three corners or the three vertices of the triangle. So that's the if black then red. Okay. It might be a little bit overwhelming because these words, like I said, are not very descriptive. The concepts are a little bit confusing as well, too, because they all seem to be saying the same thing. Something meets in the middle of a triangle, and then it's equidistant to something, so it can be a little confusing. Make sure it's in your book of truth, and it won't be too bad. All right, 2 down, 2 to go. Once again, what would happen if we had a triangle? All right, I'm not going to do angle bisectors. I'm not going to do perpendicular bisectors. Well, what's left? Well, if I go from the corners, there's one other shape I can make. I can make this thing called an altitude. And remember, an altitude of a triangle is you go to a vertex, and then you go perpendicularly down. I'll draw this for you. You go perpendicularly down to the opposite side. So pick a corner, any corner. I'll pick the lower left. If I go perpendicular to the opposite side, in other words, that's a right angle right there, then that red line, I should have made it colored blue or something. That's called a altitude. Hey, you got 3 altitudes of a triangle. Guess what happens when you draw the 3 altitudes of a triangle? That's right, they're all going to meet. So here's an interesting thing, though. We haven't talked about the fact that triangles can be acute, right, or obtuse. Well, here's the so what. It doesn't matter for the in-center or the circumcenter. That point of concurrency will always be in the middle of the triangle. It's different for altitudes. So let's think, if we have a left one first there, if we have an acute triangle and we draw the altitudes of it, yeah, you get a point of concurrency and it looks to be in the middle of the triangle as well, too. Oh, I should have pointed this out at the start. All of these point of concurrencies are all going to be different than each other, unless it's a special kind of triangle. So the in-center, the circumcenter, they don't always happen at the same spot. And this one won't happen at the same spot as well. Now let's look at the right triangle. Since we're making altitudes, well, if I go from that bottom vertex upward, it's a right angle already, right? I should have said if we go from the top vertex down, well, it's already a right angle. And if we do it from that side, well, it goes there. And if we do it from the last side, it winds up there. And if you can see, the point of concurrency isn't in the center of the triangle anymore. It's actually on the triangle. And lastly, if we make the altitudes an obtuse triangle, right, Suspiciously, we got a problem right here, and the problem is this. If you try to draw from right, let's see, from right here, this vertex right here, perpendicularly to the opposite side, well, that's not a right angle right there. That didn't work. So the only way that you can draw a right angle is that if you extend the side, and now we can make a right angle. So I'll make it prettier now. So let's see, that would look like that. And if we do it for the last vertex, that's the one on the bottom, we would have to extend that side, and it sure doesn't look like those red lines intersect unless we extend them. And if we extend them, they do meet together, but they don't meet together on the triangle or inside the triangle. They meet together outside of the triangle. All right, now that is absolutely positively not a proof of that happening, and I will prove this to you, but I will prove it to you in chapter 13. We need some other tools before we can do this. So what do you need to write down for theorem 10.3? It's simply that if you draw the altitudes of any triangle, they intersect at a point of concurrency. And that's literally what 10.3 says. What is the so what of this? There isn't a so what of this. Okay, so if the altitudes of a triangle are drawn, well, I guess the so what is that they all meet together. And it will have a name. We'll do that next. Also this, the point of concurrency does have a so what, just not in high school geometry. So if you go to college, you take a higher level geometry class, you might talk about what's the so what. All right, so what is the name of that point of concurrency? So that point of concurrency where the altitudes intersect is called an orthocenter. And if you're really super curious, you're like, oh, I really need to know what the so what is, just Google orthocenter, and you can be amazed by what the so what is about those. All right. Well, that one was easy because there isn't really a so what this year. So the altitudes are drawn. There is no so what about this. It's just that it's the orthocenter. All right, last one. Well, what's left? Let's see. We've done perpendicular bisectors. We've done angle bisectors. We just did altitudes. There's one thing left that we can do with a triangle with corners and sides. And you got to reach way back for this one. These are called medians. So remember, medians go from a vertex to the middle of the opposite side. So medians go from the vertex to the middle of the opposite side. So triangle medians, it's a line, ray, or segment drawn from the vertex of a triangle to the middle of the opposite side. I'll allow you to pause the video, write that one down. By the way, that should already be in your notes from way back when. We have done nothing with medians yet. Now we finally going to do something with medians. All right, so if I draw the medians of this triangle, this is an obtuse triangle. By the way, this will work with obtuse, right, or acute. So let's see, I need to go to the middle of that side. I need to go to the middle of that side. I need to go to the middle of that side. Yes, in fact, they do meet somewhere. This one is the most interesting one of all of them, in my opinion. So that point of concurrency is called, where the medians intersect, is called the centroid. And we get a big so what from this one. If the medians are drawn, then X, or the point of concurrency right there, is the point of concurrency. It's called the centroid. And boy, do we get a big so what. We'll write it down here in a second. All right, interesting side note before I show you the so what. If you ever make the centroid, that is where if the triangle was solid, right, then you could actually balance the triangle on your finger if you put your finger at the centroid. That's kind of a neat, interesting thing. You will use that fact in physics if you take a higher level physics course. All right, so on to the so what. All right, so we actually get some math and we get a formula from the centroid. And let's see what it is. So this is 10.4. I don't have enough that I can prove it, but I will prove it in chapter 13. We just need some extra stuff before we prove it. All right, what I want you to do is think about any triangle. And if you made the medians and therefore you make the centroid, I want you to look at each median here. If you notice, I'm going to look at AM first. We have a long piece and we got a short piece. Now look at another one, and we get the same thing. We got a long piece, and we got a short piece. And look at the last one. I'm out of colors here. We get a long piece. It's kind of, I think that's purple. And we get a short piece. So I'm going to give you a so what about the long piece and the short piece. I'm going to give you a so what about the long piece and the short piece. And so here it is. So it turns out if the medians are drawn, it turns out that it splits the median. The centroid splits the median into two parts, a long piece and a short piece. And the long piece is 2/3 of the entire median, and the short piece is 1/3. So if I were to draw that, the short piece of OC is OX, and that would be 1/3 of the entire length, and CX would be 2/3 of the entire length. And that goes for each one of those medians there. Now, I think you can see that those medians are clearly not the same length as each other, but each one is broken up into 1/3 and 2/3 of the entire length of the median itself. Pretty bold claim there. I will prove it, just not this chapter. I think this is the first time that I've made a statement that I'm not going to prove until later. Okay, so how does this mathematically work? Well, let's just look at just a generic triangle right here. I drew two. I didn't draw all three medians there. I drew two of the medians. Let's see. I've got AG as a median, and I got CF as a median. Okay, so let's see. It's supposed to break it up into small piece and large piece. So let's see. What's the small piece of CF? That would be XF. And what's the large piece? That would be CX. Okay, so we got a short piece and we got a long piece. So if we look at CF, the short piece is XF, right? There's the long piece, or there's the entire piece. That's the median. And then from the centroid, that breaks it up into short piece, long piece. So the short piece is FX, and the long piece is CX. And we know that the relationship between the short piece and the long piece is 1/3, 2/3. So 1/3 of the entire distance of CF, 1/3 of that, that's what FX is. And we know that 2/3 of the entire thing, that's what's the long piece. So 2/3 of CF, the entire thing, so 2/3, yes, we're going to do some math with fractions here in a second, is equal to CX as well too. How about the other one? So AG. Well, once again, it breaks it up into 1/3, 2/3. So let's see, the small piece is GX and the large piece is AX. Let's see, the short piece is GX and the long piece is AX. And we get that same relationship. So 1/3 of the entire median, that's 1/3 of AG, would equal to GX. And 2/3 of the entire thing, AG, would be equal to AX. Hopefully that made sense. Now, let's do some actual problem here with some numbers. All right. Before I do that, I should just point this out. Well, maybe this is obvious, maybe this is not. If you think about 1/3 and 2/3, I mean, just literally those fractions, one is double the other, or one is half of the other, right? So if you take 1/3 and you double it, you get to 2/3. If you take 2/3 and take half of it, you get to 1/3. So even though you got these ugly fractions, 1/3 and 2/3, the relationship between them is double or half of the other. All right, let me show you with some numbers here. So 1/3, 2/3. If you double 1/3, you get to 2/3. If you take half of 2/3, you get to 1/3. So if I told you that the entire length of CF, which is a median, is 30, well, how long is the short piece? Well, the short piece is 1/3 of 30. So 30 times 1/3 would be 30 divided by 3, which would be 10. And since we know that the longer piece is double the shorter piece, well, then CX must be 20. Now, I also could have gotten that by multiplying 30 by 2/3. It's kind of your choice. Let's see, multiply 30 times 2/3. 30 times 2 is 60. 60 divided by 3 is 20. All right, a more challenging problem is where, okay, this one is kind of easy because they gave me the entire median. A more challenging problem is, well, what happens if they don't give me the median, right? So here's a more challenging one. So 1/3, 2/3 of AG. So what happens if they tell me that AX is 32? So if AX is 32, some ugly math there to get the whole thing. But before you do that, why don't you just find the short piece? So the short piece, because the relationship is 1/3, 2/3, the short piece is half of the long piece because it's 1/3, 2/3. Double 1/3, you get to 2/3. So if I take half of 32, which would be 16, you got the short piece. And the entire median is the short piece, the long piece added together. So 16 plus 32 is 48. So it's a little bit easier to find the entire piece by finding the other two pieces and then just adding them together. The way these problems work is they're either going to give me the whole thing. If they give you the whole thing, then you multiply by 1/3 or 2/3. But if they give you one of the pieces parts, in other words, one of the small pieces, one of the short piece, well, then rely on the fact that the short piece is half of the long piece, so the long piece is double the short piece. Look at those numbers, make sure you understand them. The math is not that tricky, even though the fractions are kind of ugly. All right, remember we did 4 concepts. We have 4 vocabulary words. Let's see, what were the concepts? So if we make angle bisectors, we get an incenter, and the incenter is equidistant to the 3 sides. Then we did perpendicular bisectors, and we found out that they all meet together. Let's see, that was called a circumcenter, and the circumcenter is equidistant to the 3 corners. Let's see, then we did altitudes, and that was called an orthocenter, and we didn't get anything from that other than it was called an orthocenter. But the last one, let's see, how did we make the last one? Oh, we made medians. So we made medians, and the medians break themselves up into 1/3 and 2/3. So 4 concepts, 1, 2, 3, 4. We had 4 vocabulary words. Let's see, incenter, circumcenter, orthocenter, and centroid. And then, well, I guess technically we did get 4 so whats, but only 3 of them were really interesting. The orthocenter wasn't very interesting. Okay, so there's our 4 words. Nobody keeps these straight the first time you hear them. The actual individual concepts are not too bad, but keeping all this together in your head is challenging. So make sure you got everything in your book of truth. And that's it. All right, I'll end up here on the homework right here once again, but we'll end it right there. If you have any problems, send me an email.